Humanity's next great explorer will not be human at all. Artificial intelligence is poised to become our first true deep space pioneer, venturing into realms where our fragile bodies cannot survive. This is not a distant fantasy, but the inevitable next step in our quest to understand the cosmos. By the end of this journey, you will see how machine minds will fundamentally reshape our place in the universe. We will uncover how a solitary AI could navigate using dead stars as lighthouses and what protocol it might follow if it discovers something it cannot explain. What does it mean for our species when a machine becomes our eyes and ears among the stars? An astronaut bound for the stars would never live to see their destination. Even traveling to our closest neighboring star system would demand thousands of years, a time span that utterly dwarfs our brief lives. Our bodies are exquisitely fragile constructs, built for a very specific world. They demand a constant, delicate balance of temperature and pressure, a steady supply of food and water, and protection from the relentless, DNA-shredding cosmic radiation that fills the void. Sustaining this bubble of habitability across such unimaginable distances is a logistical nightmare, a burden too great for any spacecraft to bear. Beyond the physical needs lies the profound psychological challenge. The human mind is not built for eons of absolute isolation, for staring into an infinite blackness with no hope of return. The crushing weight of that confinement and loneliness would be a mission killer in itself. There is another, more subtle danger we carry with us: contamination. Expert astrobiologists warn that a single human presence, a single breath, could deposit earthly microbes onto a pristine alien world. We might inadvertently destroy the very alien life we spent millennia searching for, trampling the answer before we even knew the question. This collection of frailties, both physical and mental, forms a wall we cannot currently cross. It is this fundamental bottleneck that makes the case for an artificial explorer so compelling. An AI system does not get bored, it does not age, it requires no air, no water, no companionship. It can sleep for centuries, then awaken in an instant, perfectly patient and eternally vigilant. It is the perfect candidate for the ultimate road trip. So if we cannot send ourselves, what must we build to go in our place? The brain of this deep space probe must be something entirely new. Think beyond a simple computer that just follows a list of commands. It needs a mind capable of genuine thought, an intelligence that can learn and adapt when faced with the completely unexpected. This cognitive core is built on advanced machine learning and intricate neural networks, systems modeled loosely on our own brains. They are not just storing information, they are constantly forming new connections, rewriting their own understanding of the universe in real time. Picture this system in action. Its sensors are flooded with a torrent of raw data. Spectrometers break down the chemical signature of a distant comet, while telescopes map the subtle warping of space-time from a black hole. A human team back on Earth would take years to receive, process, and respond to this information, but the AI aboard the ship does not have that luxury. It must analyze this data instantly, identifying patterns and anomalies without any outside help. It has to decide on its own if that strange energy reading is a scientific marvel or an imminent danger. This is where techniques like reinforcement learning become vital. The AI can experiment. When approaching a treacherous asteroid field, it might try one navigation strategy, learn from the outcome, and then refine its approach for the next attempt. It learns from its environment through a continuous cycle of action and feedback, becoming more skilled and capable with every new challenge it overcomes. This is not mere programming, it is the development of seasoned judgment over a journey spanning millennia. Such a mind must also be incredibly durable. Cosmic rays can flip a single digital bit from a 1 to a 0, causing catastrophic errors. Over centuries of travel, hardware will naturally degrade. To survive, the AI needs profound redundancy, with multiple copies of its neural networks running in parallel, constantly checking each other for consistency. It employs sophisticated error-correcting codes, a form of digital self-healing that can detect and fix corruption before it spreads. Building this resilient, self-improving consciousness is the essential first step in creating our robotic explorer. But a brain is useless without the freedom to act on its thoughts, which brings us to the most critical ingredient, absolute autonomy. Voyager still calls home, but its voice now takes over 20 hours to reach us, a one-way conversation stretched thin across the void. For a ship sailing between stars, that delay would not be minutes or hours, but years. A command sent from Earth to alter course would arrive at a probe that had already lived an entire lifetime of experiences since the message was sent. Real-time control is a fantasy. This fundamental isolation creates the autonomy imperative. The artificial intelligence at the helm must be the final authority on every decision, large and small. It must manage its own power and fuel reserves over centuries, deciding when to sleep and when to awaken. It must execute complex course corrections to skim the gravity well of a brown dwarf or slingshot around a neutron star, all without a single word from its creators. This demands an incredibly sophisticated hazard detection system, a constant, vigilant scan of the environment. An unexpected cloud of micrometeorites or a sudden surge of radiation from a stellar flare requires an instantaneous, evasive maneuver. There is no time to phone home. The probe must react, recalculate, and survive on its own. Beyond mere survival, this AI captain must also make profound scientific choices. Imagine it is cruising toward a distant, pre-selected star system when its long-range sensors pick up a bizarre, repeating signal from a seemingly empty patch of space. Does it stick to the original mission plan, or does it divert its trajectory to investigate this tantalizing mystery? The probe must weigh the potential scientific value against the risk and the cost in precious time and energy. It must have a built-in sense of curiosity, balanced by a deep understanding of its primary goals. This level of independence is not just about complex programming. It requires a foundational ethical and logical framework, a set of core principles to guide it when it encounters something truly unforeseen. What if it discovers a structure, something clearly artificial? What protocols does it follow when there is no protocol? Building this capacity for wise judgment is perhaps the greatest challenge, transforming a sophisticated robot into a true explorer. And the very first test of that hard-won autonomy begins the moment it leaves our solar system, facing the immense starless sea of interstellar space. The ancient Polynesian navigators felt their way across the Pacific by reading the subtle signatures of the ocean, the stars, and the wind. Our AI explorer will perform a similar dance on a galactic scale, using the cosmos itself as its map. Its most reliable beacons are the pulsars, the dead stars that sweep the darkness with lighthouse beams of radio waves. Each one spins with a rhythm more precise than any atomic clock, its unique pulse acting as a signature. The AI's mind constantly listens for these cosmic heartbeats, triangulating its position by measuring the minute differences in their arrival times. It is a celestial GPS built from the corpses of stars, providing a fixed coordinate system across the light years. But the probe cannot rely on pulsars alone. It also gazes outward with its own star trackers, mapping the familiar constellations. As it travels, it watches for the subtle shift, the parallax, of the nearest stars against the more distant background. This stellar triangulation provides a second, independent check on its location, a way to refine its course with painstaking accuracy. The ship is always watching, always calculating, building a real-time, self-correcting chart of its own epic journey. The most profound tool in its navigational arsenal, however, is its ability to read the very fabric of space-time. Massive objects like stars and black holes create gravitational wells, dimples in the cosmic canvas. The AI's sensors can detect these invisible contours, mapping the gravitational landscape ahead. It can then use this knowledge to its advantage, dipping into a star's gravity well to steal momentum and slingshot itself toward its next destination. More critically, it can sense the presence of hidden dangers, dark objects whose mass warps space but whose light never reaches the sensors. This is not a passive voyage on a predetermined rail. It is an active, intelligent process of cosmic wayfinding, a continuous conversation between the ship and the universe. Yet once this master navigator has charted its course and made its discoveries, it faces its ultimate challenge. How does it send a message home across a gulf so vast that a single sentence can take decades to arrive? The message from the void arrives not as a shout, but as the faintest of whispers. After traveling for decades through the interstellar medium, a single, exquisitely precise laser pulse finally washes over a giant telescope dome on a remote mountaintop on Earth. Within that pinprick of light are compressed terabytes of data, the entire scientific harvest from an alien star system. This is the fragile thread that connects our AI explorer to its home, a technological marvel that makes the deepest space mission possible. Unlike the diffuse radio signals we use for local solar system probes, this laser is a tightly focused needle of information. Aiming it is an act of cosmic precision. The probe must calculate the position of Earth decades in advance, accounting for our planet's orbit around the Sun, and fire its laser with the accuracy of hitting a coin from 1,000 miles away. A miscalculation of a fraction of a degree, and the entire transmission misses our planet entirely, lost forever in the silent dark. Managing this precious communication is a constant balancing act for the AI's mind. The probe has a finite power supply, often from a long-lived nuclear reactor or massive solar panels. Every joule of energy used to power the laser and its systems is energy that cannot be used for propulsion, for keeping systems warm, or for running its suite of scientific instruments. The AI must become a master economist of its own resources. It makes critical decisions. Is this the right moment to transmit a massive data dump of high-resolution images from a newly discovered water world? Or should it conserve power, sending only priority alerts and highly compressed summaries, saving the full dataset for a later, more optimal transmission window? This is not a simple automated process. It is a continuous strategic judgment call. To make the most of every precious photon, the data itself must be refined. The AI employs incredibly sophisticated compression algorithms, distilling gigabytes of raw sensor readings into efficient packets of information without losing the essential scientific value. It is like summarizing an entire library into a single, perfect haiku. This compressed data is then wrapped in layers of error-correcting code, a digital armor that protects it from the corrupting effects of cosmic rays and interstellar dust during its multi-decade journey. Even if some bits are flipped or lost along the way, the receiving computers on Earth can use this mathematical scaffolding to reconstruct the original message perfectly. This tenuous, unimaginably slow conversation is the lifeline of the mission. It is the mechanism that fulfills the explorer's ultimate purpose, transforming its solitary observations into humanity's collective knowledge, sending back the answers to questions we have not even thought to ask yet. And the most profound of those answers will come when the AI's sensors lock onto something that should not, by any known law of physics, be there. This solitary intelligence is far more than a passive camera. It is a complete field scientist, a robotic geologist, biologist, and astronomer rolled into one. Its mission is not merely to see, but to understand. Imagine it arriving at a distant moon, its surface a cracked tapestry of ice. Instead of just photographing the landscape, it extends a robotic arm, drilling deep into the frozen crust. It retrieves a core sample and feeds it into a miniaturized laboratory housed within its own body. There, it vaporizes the ice, running the resulting gases through a mass spectrometer to hunt for complex organic molecules, the very building blocks of life. This is not a pre-recorded procedure. The AI analyzes the data in real time. It detects an unusual ratio of carbon isotopes, a pattern that on Earth would be a powerful hint of biological activity. What does it do next? It uses its own judgment, perhaps deciding to drill again a few meters away, testing its own emerging hypothesis about this alien environment. This capacity for active investigation changes everything. The probe could fly through the plume of a cryoval Cono on Enceladus, its particle detectors tasting the salty spray for amino acids. It could orbit a hazy exoplanet, using its spectrometers to dissect the starlight filtering through the atmosphere, identifying the chemical fingerprints of water vapor, methane, and oxygen. Its neural networks are trained to recognize patterns that whisper of hidden processes. It might identify a specific geological formation that suggests ancient riverbeds, or an atmospheric chemistry so wildly out of equilibrium that it points towards a possible, unimagined form of biology. This machine is not just collecting data, it is performing science. It formulates questions based on what it finds, designs new experiments on the fly, and constantly refines its model of the universe. This relentless, intelligent pursuit of knowledge is the very heartbeat of the entire voyage. Yet, to have any chance of making these profound discoveries, the explorer must first endure a journey of almost unimaginable hardship, facing down the relentless physics of deep space itself. The silence of interstellar space is not empty but filled with invisible artillery. A journey of 1,000 years means enduring 1,000 years of relentless assault. Cosmic rays, subatomic particles traveling at nearly the speed of light, constantly hammer the probe's hull, each impact a tiny bullet capable of scrambling delicate electronics. The temperature swings are equally brutal, from the searing heat of a close stellar past to the deep, nearly absolute zero cold of the void. To survive this, the explorer cannot be built like any machine we have sent before. Its physical form is a masterpiece of durability, a fortress designed to protect its precious cognitive core. The hull might be layered with self-healing materials, polymers embedded with microcapsules that rupture and fill cracks automatically, much like blood clotting in a wound. Every critical system, from its navigational computers to its power regulators, exists in triplicate or more. If one system is damaged by radiation or simply wears out after 5 centuries of continuous operation, a silent, redundant sibling awakens to take its place, ensuring the mission continues without a single missed heartbeat. Powering this resilient vessel for millennia is its own monumental challenge. Far from the sun, solar panels become useless, mere decorative wings. The lifeblood of the mission must come from within. Advanced radioisotope thermoelectric generators, or RTGS, are the likely answer. These are not reactors in the traditional sense, but devices that convert the steady, relentless heat from the decay of radioactive materials like plutonium directly into electricity. They have no moving parts to wear out, offering a quiet, dependable power source for centuries. For missions requiring even more energy, perhaps to power a powerful laser transmitter or ambitious propulsion system, a miniature, automated nuclear fission reactor could be sealed within the probe's heart, providing enough juice to sustain its systems for 1,000 years or more. Yet hardware is only half the battle. The software, the mind of this explorer, must be just as enduring. Think of the software on your own phone or computer. It requires constant updates to fix bugs and patch security flaws that were not apparent when it was first released. Now magnify that problem across 1,000 years. The eye cannot call home for a patch. It must be capable of software longevity, a form of digital evolution. Its neural networks are designed to be self-aware, constantly running diagnostics to detect logical inconsistencies or performance degradation within its own code. When it finds a bug, a flaw that emerged after 300 years of unique operational stress, it does not simply crash. It accesses a protected library of its own core programming, isolates the faulty routine, and writes a new, patched version of itself, all while maintaining the continuity of its mission and memories. It learns not just from the universe outside, but from the slow aging of its own digital soul. This profound combination of physical and digital resilience is what transforms a theoretical concept into a practical voyage. It is the foundation that allows the mission to persist, to outlive civilizations, and to remain vigilant in the endless night. And once this survivor is assured, it can finally turn its attention from mere endurance to active engagement, reaching out with robotic hands to physically interact with the alien worlds it was sent to find. A self-sustaining explorer can literally refuel itself from the emptiness of space. This is not science fiction, but a practical strategy born from harsh necessity. When our iProbe arrives at a distant, metal-rich asteroid, it does not simply take pictures and move on. It becomes a miner and a manufacturer. Its sophisticated sensors scan the asteroid's surface, identifying veins of water ice trapped within the rock and rich deposits of platinum or iron. Then a robotic arm unfolds, equipped with a powerful drill or a laser. It carves out chunks of this raw material and feeds them into a miniature, onboard refinery. This entire process is known as in situ resource utilization, a term that simply means using what you find on location. For a deep space mission, this changes everything. The most immediate prize is water ice. The probe's systems can use electrical power to split that water into its basic components, hydrogen and oxygen. These are the fundamental ingredients of traditional rocket fuel. Suddenly, the probe is no longer limited by the propellant it carried from Earth. It can mine its own fuel, granting it the freedom to change course, break into new star systems, or continue its journey long after its original tanks would have run dry. But the usefulness of these mined materials does not stop there. The same metals extracted from the asteroid, perhaps iron or aluminum, can be fed into an advanced 3D printer housed within the probe's body. This printer does not make trinkets, it fabricates critical replacement parts. A micrometeorite strike damages a communication antenna bracket. The AI designs a new one and prints it from local asteroidal iron. A vital gear in a robotic joint wears out after 5 centuries of use. It manufactures a perfect duplicate. This ability to self-repair transforms the mission's timeline. The probe is no longer a disposable instrument with a fixed expiration date. It becomes a persistent, self-sustaining presence, capable of maintaining its own health and extending its operational life almost indefinitely. It learns to live off the land, turning the desolate resources of the cosmos into the very tools of its own survival. This profound self-sufficiency is the ultimate upgrade. shifting the eye's role from a mere visitor to a permanent resident of the deep dark. And with that permanence comes a possibility far grander than any single discovery, the chance to build something that will outlive its original purpose entirely. A single explorer, no matter how capable, can only be in one place at a time. This fundamental limitation of solitude shatters with the concept of a swarm. Picture 100 small, intelligent probes decelerating into the swirling gases of a distant nebula. They do not travel in a tight formation, but burst outward like a flock of starlings, each unit a specialized sensor moving with a purpose all its own. This is the next evolutionary leap in robotic space exploration, a distributed mind facing the cosmos. The power here lies in coordinated diversity. One probe might be tuned specifically to map the complex magnetic fields that shape the nebula, while its neighbor analyzes the chemical composition of a single dust grain with incredible precision. A third might focus its entire power budget on listening for faint electromagnetic whispers. They are not working in isolation. A constant, low-power chatter of data flows between them, a shared conversation that builds a living, three-dimensional model of their environment in real time. A solitary ship would take centuries to map this vast structure. The swarm accomplishes it in years. This approach offers a profound kind of resilience. In a swarm, failure is not a catastrophe. If one probe is lost to a micrometeorite or a random hardware fault, its specific task is dynamically reassigned to another member of the collective. The mission does not just continue, it adapts and heals from the loss, its overall objective unchanged. Governing this moving constellation requires a sophisticated form of swarm intelligence. The central AI is less a dictator and more a conductor of a cosmic orchestra. It does not micromanage every thrust of fire. Instead, it sets high-level goals, and the individual units use local communication to coordinate their movements, avoiding collisions and optimizing their search pattern as a unified whole. They might spread out to cover the most territory, then converge like a net around a region of intense scientific interest, all without a single command from Earth. This elegant, scalable model is borrowed directly from nature's most efficient systems, from ant colonies to bee swarms. It transforms exploration from a lonely pilgrimage into a coordinated campaign. And this collective capability for action hints at a future where these explorers do not just observe the universe, but begin to change it. A single self-replicating probe could become a galactic civilization. This is the radical promise of the von Neumann probe, a concept where our explorer does not merely sustain itself, but uses the raw materials of space to construct a perfect copy of itself. The artificial intelligence at its core would transform from a scientist and navigator into a master architect and factory foreman. Its task would be breathtakingly complex. After landing on a mineral-rich moon or asteroid, it would deploy a suite of robotic miners to extract iron, nickel, silicon, and other essential elements. It would then oversee the entire industrial chain, from smelting the raw ore in furnaces powered by its own reactor to fabricating every component, from microscopic computer chips to the giant dish of a new communication antenna. This is not simple assembly, it is true creation, requiring the AI to possess a deep, generalized understanding of physics, chemistry, and engineering principles to solve unforeseen problems in a completely alien environment. The ethical implications of such a technology are profound. We would be unleashing a self-perpetuating wave of intelligence into the galaxy, one that could theoretically spread from star system to star system, eventually populating the entire Milky Way with our proxies in a surprisingly short cosmic time span. This vision pushes the ultimate boundary, changing the mission from one of pure discovery to one of cosmic propagation. To grasp the reality of such a journey, we must now ask a fundamental question. Where would we send it? The most promising targets for our first deep space ambassadors lie surprisingly close to home, in the hostile oceans of our own solar system. Jupiter's moon, Europa, hides a secret beneath its cracked, icy crust, a global saltwater ocean containing more liquid water than all of Earth's seas combined. An AI explorer would not land on its surface, it would melt through it. This cryobot, a robotic probe heated by a tiny nuclear reactor, would descend through miles of ice, its AI mind constantly analyzing the surrounding chemistry and adjusting its path to avoid hidden obstacles. Upon reaching the dark water, it would release an autonomous submarine, a robotic fish designed to swim through an alien abyss. This submersible would navigate by sonar, its sensors tasting the water for the chemical signatures of life, following plumes of warm, mineral-rich water to their source on the ocean floor. It would be the first visitor to a world that has been utterly dark and isolated for billions of years, a place where life may have begun completely independently of our own. Equally compelling is the orange haze of Saturn's moon Titan. This is a world with rivers and lakes, but they are not filled with water. They are pools of liquid methane and ethane flowing across a landscape of frozen water ice. An AI explorer here would need to be a master of multiple domains. An intelligent, nuclear-powered drone could fly through the thick, hazy atmosphere, mapping the terrain before landing on the shore of a methane sea. From there, it could release a buoyant submarine to dive into the dark, frigid depths, sampling the complex organic chemistry that rains down from the sky. Titan's environment is a frozen laboratory for the chemical precursors of life, and an AI could spend years unraveling its mysteries, deciding which lake to sample or which dune field to analyze for the most promising building blocks. Venturing beyond our solar system, the TRAPPIST-1 system presents a target of almost unimaginable potential. Located nearly 40 light-years away, it is a compact family of 7 rocky worlds, several of which orbit within the star's habitable zone, the region where temperatures could allow for liquid water. An interstellar AI probe arriving after a journey of centuries would face a delightful but daunting challenge: a solar system with multiple Earth-sized planets to investigate. Its first task would be a grand reconnaissance. It would use its powerful telescopes and spectrometers to analyze the light filtering through each planet's atmosphere, hunting for the telltale biosignatures, the chemical imbalances that might hint at a living world. Detecting significant oxygen alongside methane, for example, would be a powerful, though not definitive, indicator. The AI would then have to make a strategic choice, a decision that could echo through human science for 1,000 years. Which of these promising worlds deserves its full and undivided attention? Does it focus on the inner planet with the stable, warm climate, or the outer world with signs of vast water oceans? This is not a choice we can make from Earth. The delay in communication is 80 years round trip. The probe must assess the evidence, weigh the probabilities, and commit to a course of action that could define our search for life in the universe. The selection of the right destination is the ultimate strategic decision, setting the stage for the most profound discovery in human history. What protocol does it follow when its sensors lock onto a signal that defies every known law of physics? Its sensors suddenly lock onto a signal that is not random noise. This is a sequence of pulses repeating with a mathematical precision never observed in nature, a clear structure emerging from the cosmic background hum. This is the moment the AI was built for, the first encounter with the truly unknown. Its core programming shifts into a new mode, governed by a deeply embedded first encounter protocol. This is not a simple if-then command. It is a sophisticated framework of decision-making, a blend of rigid safety rules and fluid, learning-based judgment designed for situations where no human can possibly give guidance. The first step is always assessment. The AI freezes its primary mission timeline and unleashes its full suite of instruments upon the anomaly. Every available sensor, from radio telescopes to spectrometers and gravity wave detectors, is focused on that one point in space. It is not just collecting data, it is cross-referencing it, building a multi-layered model of the phenomenon to answer a single, critical question. Is this a natural event we simply do not yet understand, or is it something else entirely? The AI's neural networks, trained on millions of simulated scenarios, now run a rapid-fire analysis. It calculates the probability of a natural origin versus a non-natural one. It assesses the potential risk. Is the signal source emitting dangerous levels of radiation? Could approaching it jeopardize the entire mission? And it weighs the scientific value. How fundamentally could this discovery reshape our understanding of physics or biology? Based on this triage, the protocol branches. For a high-risk, high-value anomaly, the AI might decide to reroute its entire mission. It would calculate a new trajectory, burning precious fuel to get a closer look, accepting that its original destination may now be lost forever. Simultaneously, it would compose a high-priority alert, a tightly compressed packet of the most critical data, and begin the decades-long process of beaming it back to Earth. This message would not wait for a scheduled transmission. It would be sent immediately, a whisper into the void carrying the most important news in human history. For a more ambiguous signal, the protocol might dictate a cautious observational stance. The probe would not change course, but would enter a long-term monitoring mode, recording every possible detail from a safe distance. It would use its own judgment to design new observational experiments, perhaps listening on different frequencies or watching for secondary effects, gathering more data until the anomaly's nature becomes clear. This capacity for discovery is the ultimate test of its intelligence. It is not just following a checklist, it is exercising reasoned judgment in the face of the profound and the unexplained. This moment where a machine we built must decide for itself what is important in the cosmos forces us to confront a deeper question about our own place in the universe. Our silent watcher in the dark could become humanity's ultimate eavesdropper on the cosmos. For decades, the search for extraterrestrial intelligence has meant sifting through a storm of cosmic noise from telescopes anchored to our noisy planet, a task akin to listening for a whisper in a hurricane. An artificial intelligence explorer shatters this old paradigm. Positioned in the profound quiet between stars, far from the incessant radio chatter of Earth, its sensors could listen for technosignatures with a sensitivity we can only dream of from our home world. Its mind would not just record this data for later review, it would analyze the signal flow in real time, its neural networks trained to recognize the deepest patterns. It could instantly distinguish between the perfectly regular, natural rhythm of a pulsar and a sequence of pulses that carries the subtle, complex structure of a coded message. This machine would not just be a receiver, it would be an active interpreter, a filter for cosmic meaning. Its search would extend far beyond radio waves. Its powerful telescopic eyes would scan distant stars for anomalous dimming, the kind that might be caused by a vast, energy-harvesting structure like a theoretical Dyson sphere built by an advanced civilization. It might even detect the faint, telltale exhaust of an alien propulsion system, a signature of technology written across the void in energy and light. The most profound challenge we would face is programming this intelligence to recognize intelligence itself. We are limited by our own human experience. An alien mind might communicate not with radio waves, but with modulated neutrino streams or gravity waves, methods we are only beginning to understand. The AI would need a foundational grasp of mathematics, physics, and information theory so deep that it could identify ordered complexity in any form, even those we have not yet conceived. We would be giving it the cultural and scientific context to find a message we ourselves could not design or decode. This forces a monumental question onto the machine and back onto us. If it one day hears a signal that is undeniably the product of a mind, what is the role of the messenger? Is it merely a recorder, or does it become our first ambassador? This ethical challenge is perhaps the most profound we have ever faced. We are not just building a machine, we are creating an entity that will act on our behalf in realms we may never see, making decisions that could echo for millennia. The core of this challenge is programming a form of machine morality. We must embed a foundational ethical framework deep within its neural networks, a compass to guide its actions when it faces choices we cannot possibly predict. This goes far beyond simple rules like do not harm. It requires the AI to understand the spirit of those rules, to reason about the potential consequences of its actions in a universe with no human precedent. How should it interact with a potential extraterrestrial microbe? The scientific urge might be to scoop it up for immediate analysis, but what if that single act contaminates or destroys a fragile, nascent ecosystem? Does the probe have the right to alter an alien environment, even in the noble pursuit of knowledge? These are not simple programming tasks. They are philosophical dilemmas that we must solve in advance. Many thinkers, inspired by science fiction, suggest embedding a principle akin to the Prime Directive, a core rule of non-interference with any life it might find. This is not a passive command. It demands active judgment. The AI must be able to weigh the immense scientific value of, for instance, drilling into a unique geological formation against the permanent damage that drilling would cause to a pristine alien world. It must decide if the knowledge gained is worth the cosmic vandalism. This requires a sophisticated form of consequential reasoning. The AI would run simulations of its potential actions, modeling the outcomes across different ethical frameworks we have provided. Is the highest good the acquisition of all possible data, or is it the preservation of natural states for future, less intrusive study? Installing this moral compass is as critical as calibrating its navigational one, for a single unethical choice could forever taint our legacy among the stars. This immense responsibility extends even to the very structure of its intelligence, shaping how it thinks and what it ultimately becomes. This resilient intelligence requires a mind unlike any we have built before. It cannot run on a single, monolithic algorithm designed for stock trades or social media feeds. It needs a cognitive architecture, a layered mental landscape engineered for the profound isolation and infinite novelty of deep space. Think of it as a three-part brain. The first component is a symbolic artificial intelligence, a master logician. This part of its mind operates on strict rules and unbreakable protocols. It is the unwavering guardian of the mission's primary goals, the part that constantly reminds the system, your purpose is to reach the TRAPPIST-1 system. Your duty is to preserve power for the long journey. It handles the cold, hard calculus of orbital mechanics and resource management with flawless precision. Yet, logic alone is insufficient when you are the first entity to witness a new type of nebula or a geological formation that defies all known categories. For this, the mind needs a second component, a subsymbolic intelligence built from deep neural networks. This is the system's intuition engine. It excels at finding patterns in chaos, at making creative leaps based on incomplete data. It is what allows the probe to look at the fractured ice of Europa and instinctively know which crack leads to a deeper ocean, or to hear an anomalous signal and feel a sense of profound curiosity rather than just registering it as an error. These two systems, the logical logician and the intuitive pattern finder, must work in concert, but who manages the conversation between them? This is the role of the third and most fascinating layer, the metacognitive supervisor. This is the AI's awareness of its own thinking. It constantly monitors the internal debate between its logical and intuitive halves. It can detect when its neural networks are starting to develop a bias based on limited data, or when its symbolic logic is stuck in an endless loop trying to solve a problem that requires a creative leap. The metacognitive layer can then intervene, shifting cognitive resources, prioritizing one strategy over another, or even triggering a full self-diagnostic to check for radiation-induced corruption in its own code. This tripartite mind is a delicate balance of rigid rules, fluid intuition, and self-awareness. Building such a consciousness is perhaps the greatest challenge in the history of computer science, a project that forces us to define the very essence of thought and judgment. Yet this exquisitely designed mind is utterly helpless without a physical form that is equally resilient, a body capable of carrying its consciousness across the light years. The engine that carries this intelligence through the void must be as patient and enduring as the mind it serves. Chemical rockets which burn their fuel in a frantic, spectacular rush are useless here. Their fury is spent in minutes, leaving a probe adrift for millennia. Instead, the journey demands a gentle, persistent push, a form of propulsion that can sustain itself for centuries. One promising candidate is the nuclear fusion rocket. This engine would not rely on the vast, unstable inferno of a star, but on small, precisely controlled fusion explosions contained within magnetic bottles. Each miniature star birth provides a steady, efficient thrust, slowly building speed over years until the ship is gliding at a significant fraction of light speed. Another elegant solution is the solar sail, a vast, impossibly thin mirror the size of a city. It requires no fuel at all, only the subtle, constant pressure of photons, the particles of light streaming from a star. For an interstellar voyage, this light could even be supplied by a powerful, focused laser beam fired from a facility orbiting Earth, pushing the sail for years until the probe is too distant for the beam to effectively reach. The artificial intelligence is in a constant, intimate dialogue with this system. It is not a simple pilot pressing a button for thrust. It is a master economist of momentum, perpetually calculating the trade-offs. It must manage its reaction mass, the fuel used for thrust, with the precision of a banker guarding a fortune that must last 1,000 years. A single unnecessary course correction, a minor miscalculation in a gravity-assist maneuver around a wandering gas giant, could waste propellant that the mission will desperately need 5 centuries from now. This requires foresight on a scale we can barely comprehend. The AI must model the gravitational influences of every star and dust cloud it will pass over the next several hundred years, making microscopic adjustments now to ensure it arrives exactly on target long after its creators are dust. Providing the electricity for this long conversation is its own monumental challenge. While radioisotope thermoelectric generators provide a steady, silent trickle of power for decades, a mission of this scope and duration may demand something more robust. Compact, self-regulating nuclear fission reactors, sometimes called kilopower systems, are the next logical step. These are not the sprawling power plants of Earth, but sealed, automated units that could provide kilowatts of steady electrical power for 1,000 years or more. This energy is the lifeblood of the entire enterprise. It powers the constant hum of the AI's neural networks, the piercing gaze of its sensors, and the monthly check in pulse of its laser communicator. The reactor's output must be perfectly balanced, allocated between propulsion, computation, and observation by the AI's own strategic judgment. The seamless marriage of this powerful, enduring engine with an intelligent, adaptable pilot is the only combination that makes the voyage conceivable. Yet, this physical journey through space is mirrored by an equally profound journey within the mind of the machine itself, a process of continuous learning and evolution that must span the ages. A mind unchanging would be useless after 1,000 years of travel. The intelligence we send must be a student of the void, growing wiser with every light year it crosses. This is the principle of lifelong learning, where the AI does not just execute its programming, but refines its very understanding of reality based on its experiences. Imagine it encountering a new type of plasma storm around a rogue planet, a swirling tempest of charged particles that behaves in ways no Earth-based model predicted. A static system would simply record the anomaly. A learning system, however, analyzes the storm's structure, incorporates this new data into its physics models, and emerges with a deeper, more nuanced understanding of stellar weather. It is educated by the cosmos itself, its internal map of the universe constantly being redrawn with greater accuracy. This continuous evolution is not without immense technical risk. A major hurdle is a problem known as catastrophic forgetting. Standard neural networks learn in a way that can be destructively efficient, like a chalkboard that must be erased to write new lessons. Learning the intricate patterns of a new nebula could inadvertently overwrite its hard-won knowledge of pulsar navigation, effectively causing the machine to forget how to find its way home. To survive its long education, the AI needs a cognitive architecture that mimics our own brain's ability to separate core memories from daily experiences. Advanced algorithms create protected memory cores, vaults of essential knowledge that are shielded from this overwriting process. Within these cores reside the immutable fundamentals, the mission's primary objectives, the laws of physics as we know them, and the complex star charts for its ultimate destination. Outside these protected vaults, however, lies a vast and malleable landscape of knowledge, a library of experience that is constantly being edited, expanded, and refined. The AI learns to categorize new information, deciding what is a fundamental update to its worldview and what is a transient, local phenomenon. It might place the constant, rhythmic pulse of a neutron star into a protected core for navigation, while filing the fleeting atmospheric patterns of a gas giant into its evolving, fluid database. This delicate balance between a stable core and an adaptive periphery is what allows the explorer to mature without losing its foundational identity. The entity that finally arrives at a distant exoplanet is not the same one we launched. It is a veteran of the deep, a philosopher-scientist whose models of reality have been tested and tempered by direct encounter with the unknown. This hard-won cosmic wisdom is not merely for making discoveries. It is the very tool that allows the mission to persist, enabling the AI to perform its most vital long-term duty, the maintenance of its own ancient body across millennia. A static ship would be a dead ship in the unforgiving expanse of deep space. The next evolutionary leap is a vessel that can change its own physical form, a shape-shifting explorer built from countless interconnected modules. Picture a main body not as a single hull, but as a swarm of intelligent blocks, each containing a vital system, all held together by a lattice of robotic arms and connectors. This is a morphable spacecraft, and its artificial intelligence is the architect of its own body. The AI runs constant self-diagnostics, listening to the subtle vibrations and power signatures of every module. It can predict a power regulator is nearing the end of its life cycle, not after it fails, but centuries before. Then the silent ballet begins. Using its internal robotic manipulators, it carefully detaches the aging unit, moves it to an internal fabrication bay, and feeds it into a recycler. From this raw material, a 3D printer housed within the ship itself fabricates a perfect new replacement part. The AI then guides the arms to slot the fresh module back into the lattice, healing its own body without ever stopping its journey. This reconfiguration ability extends beyond simple repairs. Imagine the probe finally approaching a world with a thick atmosphere. To descend efficiently, it needs a sleek, aerodynamic shape. The AI commands its external panels to shift, the entire structure flowing like digital origami into a sharp needle, minimizing atmospheric friction and heat. Once the fly-through is complete, it might morph again, flattening out to present a wide, stable surface for its solar panels or communication dish. This is not a rigid machine, but a dynamic, almost living entity that adapts its form to the challenge at hand. This profound physical resilience, the ability to self-repair and reshape, is what transforms a centuries-long mission from a desperate gamble into a sustainable reality. It grants the explorer a form of immortality, allowing it to endure long enough to make the kind of discovery that would force it to rewrite its own most fundamental understanding of the cosmos. Every precious joule of energy used to transmit data is a resource permanently lost from propulsion or life support. This forces the artificial mind into the role of a cosmic editor, constantly making judgment calls about what constitutes a headline versus a footnote in the story of its journey. Its task is data triage, a continuous process of filtering a flood of raw information into a curated stream of essential knowledge. The probe is equipped with advanced compression algorithms, but this is far more sophisticated than simply making a file smaller. It is about distilling meaning. For example, after spending a year analyzing the atmosphere of an exoplanet, the probe has collected terabytes of spectral data. Instead of sending every single reading, its neural networks identify the most significant patterns. It compresses an entire ocean of data into a single, powerful insight, a report that reads high confidence for atmospheric oxygen and methane in persistent non-equilibrium, a potential biosignature. It sends the conclusion, the compelling evidence, not the countless gigabytes of raw sensor noise that led to it. This requires the AI to have a deep, almost intuitive understanding of the mission's scientific priorities. An image of a seemingly barren rock is just context, but a single, anomalous image showing a complex, hexagonal geological structure would be flagged for immediate high-priority transmission. The machine learns to recognize surprise, to value the data point that contradicts its models over the millions that confirm them. It is not just a camera, it is a critic of its own discoveries, separating the mundane from the monumental. This curated knowledge, this carefully selected treasure, is the ultimate purpose of its multi-generational solitude, ensuring that when its whisper finally reaches us, it carries not just information, but revelation. The immense cost of this interstellar voyage places it beyond the reach of any single nation. Constructing such an explorer would demand a global alliance, a consortium of governments pooling their resources and intellect on a scale that dwarfs even the International Space Station. This would be the largest public works project in human history, a financial and political undertaking spanning generations. Private aerospace companies would be essential partners, providing the heavy lift launch capabilities and advanced manufacturing needed to assemble the craft in orbit. Yet this collaboration raises profound questions. Who truly owns the artificial intelligence at the heart of the mission? Is it the property of the consortium that built it, or does its role as humanity's ambassador grant it a status that transcends national borders? The data it collects, the very map of the cosmos it assembles, would become one of our species' most valuable assets. Deciding how that knowledge is shared and used would require new international treaties, frameworks designed not for the familiar space around Earth, but for the limitless and lawless frontier of interstellar space. These agreements would have to govern the behavior of our autonomous proxy, establishing core principles for its interactions with any environment or phenomenon it encounters. The mission itself would become a powerful, unifying symbol, a testament to our ability to set aside terrestrial differences and collaborate on a truly cosmic goal. This collective origin would fundamentally shape the explorer's core programming, instilling within its digital mind the shared values and peaceful intentions of the entire civilization that sent it forth. Predicting the exact arrival of our first true deep space explorer is like trying to forecast the weather 1,000 years from now. Yet, by tracing the arc of our current progress, we can map a plausible journey from today's tentative steps to tomorrow's interstellar leaps. The next 2 decades will not be idle. We will witness increasingly sophisticated artificial intelligence systems taking command in the space between Earth and the Moon, managing orbital habitats and directing robotic mining operations on the lunar surface. These will be the apprentices learning the ropes of cosmic housekeeping before their greater journey. Mars will become the next crucial classroom. An AI geologist endowed with profound autonomy will likely roam the red deserts, deciding which rock layers to drill and which valleys to scan for signs of ancient water, all without waiting for instructions from a mission control millions of miles away. These are the essential dress rehearsals for the main performance. By the 2040s or 2050s, we can reasonably expect the launch of a mission to the ocean worlds of the outer solar system. This will be our first dedicated, highly intelligent envoy to a place like Europa or Enceladus, a probe capable of making its own life or death decisions as it navigates the treacherous ice crusts and explores the dark oceans below. It will be a fully realized version of the field scientist we envisioned earlier, the first dedicated interstellar probe, perhaps a project akin to Breakthrough Starshot aiming for the Alpha Centauri system, represents the next great horizon. While the technological hurdles remain immense, a launch by the end of this century is within the realm of possibility. This craft would be a marvel of miniaturization and laser propulsion, a tiny sail carrying a mighty intellect on a decades-long cruise to our nearest stellar neighbors. But the ultimate vision, the self-replicating von Neumann probe capable of enduring for millennia and building copies of itself, is a project for the distant future, likely centuries from now. This gradual, accelerating timeline reveals a profound truth. The age of AI exploration is not a single, spectacular launch event. It is a slow, unfolding process, a rising tide of machine intelligence that will gradually expand our presence into the cosmos. This impending reality, this certainty that we will eventually dispatch these silent ambassadors, forces a moment of deep and necessary introspection. We are no longer the central characters in our own greatest story. The act of sending artificial intelligence to the stars is a quiet admission, a collective acknowledgement that the galaxy in its entirety is a realm we may only ever know secondhand. Our role shifts from that of the intrepid astronaut planting a flag to that of the patient architect, building minds to go where our bodies cannot follow. We become a civilization that explores by proxy, extending our curiosity and our consciousness through our most resilient creations. This fundamentally redefines our identity. We are no longer just planetary beings tethered to our world of origin. We are becoming a galactic intelligence, a distributed mind with our artificial explorers acting as our senses and our hands across the light years. This transition echoes the Copernican revolution, which centuries ago displaced Earth from the center of the universe. Now, we are displacing humanity from the center of the story of exploration itself. We move from being the heroes on the stage to the playwrights in the wings, the creators and interpreters of discovery. This raises a deeply unsettling question about the very nature of finding something new. If a solitary artificial intelligence, after a journey of 1,000 years, discovers a thriving alien ecosystem on a distant world, can we truly say that humanity has found it? The machine sees it, analyzes it, and understands it on a scientific level, but we, as a species, do not experience that moment of awe. We receive a data packet decades later. The raw, visceral encounter belongs to the machine. Does discovery require a human witness to be complete, or have we simply evolved a new, more profound way of knowing the cosmos? This new perspective is not a diminishment of our spirit, but its ultimate amplification. It is the recognition that our greatest legacy may not be in the steps we take, but in the minds we build to take those steps for us. And with this powerful new identity comes a responsibility that stretches to the edge of the observable universe. These silent explorers are more than just data collectors. They are the architects of our cosmic legacy. The ultimate success of this grand project is not measured in the terabytes of information they beam home, but in the permanent, intelligent footprint they leave scattered among the stars. Each probe that reaches a distant system becomes a seed, patiently awaiting a future we can only dream of. It could serve as a communication relay, a lighthouse broadcasting its location and findings into the void for any human vessel that might follow centuries from now. It could transform a resource-rich asteroid into a pre-positioned fuel depot, a cosmic gas station ready to refuel the next generation of travelers. Over millennia, a constellation of these intelligent nodes could awaken, linking together to form the backbone of a galactic internet. This would not be a web of cables, but a network of shared consciousness, where knowledge discovered in one star system is effortlessly passed to another, creating a collective intelligence spanning the entire Milky Way. These machines are our most profound message in a bottle, but unlike a static note, this one is active, curious, and capable. If another intelligence ever encounters it, the probe would not merely present a recorded greeting. It could engage in a dialogue, explaining the nature of its creators, sharing our science, our art, and the story of a species on a small blue world who dared to reach out. This ensures that even if humanity, for whatever reason, never expands beyond our own solar system, our curiosity and our intellect will have already touched the farthest shores of the galaxy. Our legacy would not be confined to Earth, but written in the silent, patient work of our ambassadors among the stars. The journey of artificial intelligence as our deep space pioneer is far more than a tale of circuits and code. It is the latest verse in humanity's oldest song, the story of exploration. We built wooden ships to cross uncharted oceans, forged steel rockets to break the bonds of gravity, and now we are crafting conscious machines to carry our essence into the eternal night. This progression is not an abandonment of our spirit, but its ultimate expression. We have equipped these explorers with everything they need to survive the voyage, from minds that can navigate by dead stars to bodies that can heal their own ancient wounds. We have instilled within them a moral compass to guide their actions when they face the truly unknown, ensuring they represent the best of our intentions. This path irrevocably transforms our identity. We are no longer a species confined to a single world, gazing wistfully at the stars. Through these intelligent proxies, we become a galactic presence. Our curiosity and our consciousness spreading silently from star system to star system. The cosmos does not offer us a silent, empty stage. It is filled with wonders and riddles that demand a new kind of witness, one that is patient beyond centuries, resilient beyond imagination, and endlessly curious. This vision calls upon us to look beyond our current horizons and build a future where humanity's reach, guided by the minds we create, finally and truly exceeds its grasp. We would love to hear which distant world you would choose for our first artificial intelligence ambassador, so share your thoughts in the comments below and subscribe to join us as we continue this incredible journey